Now I want to talk about how we can co-modulate protein production and degradation simultaneously to achieve desired dynamics. Here we have simple two gene regulatory network. Note that I have this notation x arrow y and the subscript gene is not included for simplicity. From now on, we will use this simplified notation. X and Y in this case are used to represent gene. And here on the graph, X and Y are used to represent protein concentration. Please note that difference. Earlier, I mentioned that if you assume this X protein concentration is constant and that value is X, then we can say our protein concentration as time approaches infinity is equal to P sub xy times this large X, which is the constant X protein concentration, and 1 minus Py. So this is production parameter and this is degradation parameter. Now, what I want to show you is that this steady state level can be achieved with different sets of pxy and py values. In other words, same steady state level can be achieved using different sets of production and degradation. For example, let's say p sub y is 0.9 and py is 0.1. So we have strong degradation and we have also strong production, because later we will see that we have pxy which is equal to 0.1 and py which is equal to 0.9. So compared to this, we have strong production and strong degradation in case 1. Now, what is this y infinity or steady state value for case 1? We have pxy which is 0.9 and x and over 1 minus 0.1, which is also 0.9. This value is basically 0.9 over 0.9 times x. So 0.9, 0.9 cancel out and we are left with x. The steady state level is x. How about this one? In case 2, we have weak production. You see this number is much smaller than this. Now, p sub y is 0.9 and this is weak degradation. So y of infinity or the steady state level becomes pxy which is 0.1 times this constant value x over 1 minus 0.9 which is 0.1. So this value cancel out and we get x again. So here we had x, here we also have x. So what does this mean? This means that when we have different sets of production and degradation going on, we can still achieve same steady state level. In this case, for case 1, we have a strong production, so a lot of protein molecules are produced, but at the same time, a lot of protein molecules are degraded. So the final net protein amount or concentration that we get is this x. And in case 2, a small number of protein molecules are produced. However, small number of protein molecules are also degraded. And we again have this large x. So what can we achieve by co-modulating pxy and py or production and degradation? Here we have low production and low degradation. In other words, this pxy value is low and py value is also low. Let's call this level 1. And let's say we want to go from level 1 to another level, which is level 2. Now, if we want to go from here to here, the obvious thing that we want to do is increase this production rate. So in other words, we will have this high production, and the high production probably will start at this point. The high production will continue to maintain this steady state level. Now, what if we want to go from this level 1, to this level 2, much faster. One approach we can think of is this. Instead of having low production and low degradation for level 1, we have high production and high degradation. Even though we have high production and high degradation, the level will be same as the one that we had before using low production and low degradation. But in this case, when you go from 1 to 2, our high production does not change, but we have a low degradation. And how is this possible? One thing that we need to consider is that there's an asymmetry between production and degradation. Production is a slow process, and degradation is a fast process. Think about making a computer. When you make a computer in a factory, the process is very long, right? There are many steps involved in making parts and assembling those parts and so on. How about breaking a computer? If you just throw the computer far away, it may break, right? So breaking is actually a much faster process. It's same for protein dynamics. So making protein molecules is a long process. Protein molecules are made not in like milliseconds or seconds. It takes minutes and hours. Sometimes several hours for a gene to be expressed to make protein molecule. So it's a very slow process. On the other hand, protein degradation is much faster. Here I have another example of comodulation. So let's say this is the protein dynamics that you have, but what if you want to change that into something like this? We have the same steady state level like this, but we basically decrease our response time. So it reaches steady state much faster. We have this red tau to represent response time for new dynamics, and we have this black tau that represents response time for the current dynamics. Now, we know that by decreasing piece of Y or increasing degradation, protein degradation, the response happens faster. We have this plot here, and what if we decrease piece of Y? We will see something like this. And the response time will be tau. The point I'm trying to say is we can achieve fast response, and this response time is now small. But the problem is we have also decreased the steady state. Basically, the level drop. How about if you increase p sub xy while your py is still low? So your degradation is high and your production is also high. If you do that, you can have something like this, which is this dynamic. Response time is small. That means your response is fast. And also your steady state level is high. So by comodulating pxy and py, we can achieve the dynamics that we want.